Hello and welcome back. For this video, we're going to discuss mainly recursive formulas, but we are going to talk about explicit formulas. We're going to calculate terms in sequence using recursive formulas, and we're going to write geometric and arithmetic sequence recursively and then use them to model situations. But we are also going to use explicit formulas along with recursive formulas. Okay, so the first thing we're going to look at is what is an explicit formula. It's a formula that allows you to find any term of a sequence by using a formula in terms of n. For example, if I have the following sequence, 3, 5, 7, 9. So this is the first, second, third, and fourth term. And this is arithmetic because the difference between 3 and 5 is a plus 2, and the difference between 7 and 5 is a plus 2. So what if I wanted to find the 50th term? One thing we definitely don't want to do here is to go through the 5th term, the 6th term, the 7th term, all the way up to the 50th term. That would take too long. So we write a formula that allows us to jump from 4 all the way up to the 50th, and we do that with something called an explicit formula. It allows us to skip everything between. Now, a recursive formula allows you to find the nth term of a sequence by performing operations to one or more of the preceding terms. So if you use the same example as above, if I want this again, this is 1, 2, 3 in the fourth term. If I want to find the 7th term, I would just put a 5, a 6, and a 7, and I would just add 2 here, and I would get 11. Add 2 here, I get 13, and I'd add 2 here, and I get 15. And that repeated pattern of adding the same number over and over again is called recursion, and we create a formula to represent that called the recursive formula. Okay, so now we're going to find the recursive formula, or use a recursive formula of an arithmetic sequence. They want us to find the first 5 terms of the sequence. A sub 1 is the first term, and this is the actual formula right here. And this formula works real simply. To find the next term, you simply take the previous term and add the common difference. So this right here is the next term, then n minus 1 is the previous term, and then here's my common difference. Appears to be a negative 9, so they put minus 9 instead of plus negative 9. And it says if n is greater than 2. Now the reason they said if n is greater than 2 is because they gave us the first term in the sequence. So I've got the first term, which is 7. All I got to do is find 2, 3, 4, and 5, and that would be found by doing the recursive pattern. To go from 1 to 2, to find a sub 2, we're going to find a sub 2 minus 1, which again is the first term, and then minus 9 from it. So a sub 2 is equal to the first term, which was 7, and then we're going to minus 9, because this is the first term. 7 minus 9 is negative 2. Now, this is the actual formula, but we don't usually use that formula that way to calculate these because all we do is subtract 9 to get the next term. To go to the next term, we're going to subtract 9, we get negative 11. Then we're going to subtract 9, and then we get negative 20. And then we subtract 9 again, and we get negative 29. And then this is our first 5 terms of the sequence. Now we're going to use a recursive formula of a geometric sequence. And geometric sequences are really just exponentials in disguise again. But it's very similar to the previous one, the arithmetic. To find the next term, all we got to do is take a previous term and multiply it by the common ratio. So we're using a ratio, which is a multiplier instead of an addition. So it's previous times common ratio. And here's the formula right here. This part of it is the next term. The a sub n minus 1 is the previous term. And the 3 is the common ratio. So it's tripling each time. And we're just finding all the n's greater than or equal to 2. So a sub 1, the first term, they already gave it to us, it's 5. To find the next term, we take the previous term, which is 5, and times it by the common ratio of 3. We end up with 15. To find term number 3, we go to term 2, which is 15, and times it by the common ratio, and we get 45. To find term number 4, we go to term number 3, which is 45, which they don't have there. So the fourth term minus 1 is 45. So I'm going to substitute this whole expression with 45. So I have 3 times 45 now, which will give me 135. And then find the fifth term, we're going to go to the fourth term. So 5 minus 1 is fourth term. So I'm going to substitute this with the previous term of 135. So 135 times 3, that leaves me with 405. So the first 5 terms are 1, 2, 3, 4, and 5 written right there. Okay, so writing recursive formulas are very easy. First thing I want to point out, when we got arithmetic and geometric, notice we have a sub n in both cases. We have an a sub n minus 1 in both cases. And the only difference between writing these two formulas is on an arithmetic sequence, you're adding the common difference, and on a geometric sequence, you're multiplying by the common ratio. So you got to find out what the common difference is and the common ratio is to be able to write the recursive formulas. Okay, we want to write a recursive formula using a list. First thing I got to find out is this thing arithmetic or is it geometric? And if I subtract my terms here, I get 32. If I subtract here, I get 96. So as soon as I do the first two subtractions, I can realize that this is not arithmetic. So it's not arithmetic. So what I'm going to do is try and test it for geometric, so divide. So 48 divided by 16 gives me 3. 144 divided by 48 gives me 3. And just test it the last time, make sure, get 3. So this is geometric. So all we got to do is write the original recursive formula. So a sub n is going to equal r times a sub n minus 1. And the only thing we need to change in this formula is the r value, which is 3. So the recursive formula would be a sub n equals 3 times a sub n minus 1. So an explanation of this is the next term. This right here is going to be the previous term, and this is the common ratio. We can also write a recursive formula using a graph. Now we're checking the output values with their y values, so I'm going to check for arithmetic first. So 84 minus 109 is a negative 25. 59 minus 84 is negative 25. I'm going to test it one more time. So 34 minus 59 is negative 25. This thing appears to be arithmetic. That means I'm going to take a sub n equals a sub n minus 1 plus the common difference. So the only thing I'm changing about this formula is the common difference. So a sub n equals a sub n minus 1. And the common difference is negative 25. So instead of putting plus negative 25, I'm just going to write minus 25. So again, this is the next term. This right here is the previous term. And this right here is the common difference. All right, for our next example, they want us to write recursive and explicit formulas for this function. Now, the first thing I'm going to do is test to see if this thing is arithmetic or geometric. I'm going to test for geometric first, and one of the reasons I'm going to do that is you'll see that these numbers get big really fast, so I have a suspicion it's geometric. So 12 divided by 3 will give me 4. 48 divided by 12 will give me a 4. And 92 divided by 48 is going to give me a 4. And 768 divided by 192 is going to give me 4. So it looks like my common ratio, my r value, is equal to 4, and this is geometric. Now the recursive formulas are easy, so if you write down the recursive formula, all we got to do is substitute the r with 4, and our recursion is done. So a sub n equals 4 times a sub n minus 1. So our recursive formula is finished. Now, they do want us to write an explicit formula. Now, remember, the explicit formula, its advantage is to be able to jump way ahead. So, for example, if I wanted to find the 6th term, well, I would just multiply by 4 to get the 6th term. But what if I wanted to find the 50th term? I'd have to jump way forward to the 50th term, and doing this recursive process of multiplying 4 each time would take a very long time. So let's write the explicit formula. Now, let's take a look at a pattern here. So we started with our first term of 3. To get from 3 to 12, we took 3 and multiplied it by 4. To get from 12 to 48, we took 3 and times it by 4 and times it by 4 a second time. And then from 48 to 192, we took 3 and times it by 4, times it by 4, and times it by 4. And you'll start to see a pattern here. 3 times 4 times 4 times 4 times 4. And here's where the pattern comes in. Notice that this is term number 2, but you only see 1 4. This is term number 3, and you see 2 4s. Term number 4 and 3 4s. Term number 5 and 4 4s. So in each one of these instances, you still had common ratio of 3, but you had different amounts of multiplying by 4. So this 4 is our base number. So we're going to take 3 and times it by our base number. And the first one had 1 4, but a term of 2. And it looks like it's 1 less than the term. And the second one, or the third one, had 2 4s, but a term number of 3. So it looks like the number of 4s we're using is always 1 less than the term. So that would be raised to the n minus 1 power, and then all I got to do is put my a sub n. So this is how we get our explicit formula, and this will allow me to jump to any term within the sequence, where I have my first term here, my common ratio here, and I'm always subtracting 1 from the term position. So what does that formula look like? Well, that would be a sub n equals the first term times the common ratio raised to the n minus 1. So this is the formula for the explicit version of geometric sequences. You might want to write that one down. And our last example wants us to translate between recursive and explicit formulas. So the first one, they give us a explicit formula. This is actually arithmetic. And the reason I could tell that is because it looks like a linear equation, and linear equations are arithmetic. So write a recursive formula. So recursive formula is the only thing we need to figure out is the common difference. Well, the common difference, as we found out in a previous lesson, is the slope. So all I got to do is write my d as 0.5. So the recursive formula here is a sub n equals a sub n minus 1 plus 0.5. And that's our recursive formula. On the next one, they want us to write an explicit formula, and that's coming from, this one appears to be right here. This appears to be geometric because we're timing by a common ratio. So in order to do a geometric sequence, remember that one was a sub n equals the first term times r to the n minus 1. We need to find the first term and the common ratio. Well, we know what the common ratio is right here, and we can see the first term is 1011, so that formula is simply a sub n equals 1011 times 1.25 raised to the n minus 1, and this is our explicit formula for that geometric sequence.